So this is going to be a quick introduction to something called scientific notation for grade 9 advanced science or possibly grade 11 chemistry if you need a refresher. The word notation means a way of writing things, and so what we're going to be looking at here is a way of writing numbers. Scientific notation means that this way of writing numbers is commonly used in science classes in physics and chemistry, engineering, biology also. So it's a way of writing numbers in science. To begin, let's take a look at something that we should be familiar with, the idea of powers, and specifically powers of 10. So when you see something like 10 to the power of 4, if you had to explain to somebody what that meant, you'd probably say it means to take the number 10 and multiply it by itself 4 times. That's what most people in middle school years are taught. So 10 times 10 times 10 times 10, that's going to give you 10,000. Okay, so the number 10 to the 4 means 10,000. The number 10 to the 3 likewise would mean, if you explained it to somebody, 10 times 10 times 10 3 times. That's what the exponent 3 means. So that would be 1,000. Okay, so just to remind yourself, this entire thing, 10 to the power of 3, is referred to as a power. The number 3 is the exponent in that power, and the number 10 is the base in that power. So 10 is the base, 3 is the exponent, 10 to the power of 3, that entire thing is referred to as a power. So this is a bit of math review. If you keep going, 10 to the power of 2 would be 10 times 10. That would be 100, right? And then you get 10 to the power of 1, and so, okay, well, this just means 110, so just a 10. So that's just going to be 10 by itself. So this is how powers are introduced in middle years, where the exponent is thought of as the number of times to multiply the base by itself. So 10 to the 4, take the base, 10, and times it by itself 4 times. Now if you look at my pattern, 4, 3, 2, 1, you can predict that if we did this again, we'd get something called 10 to the power of 0. Now if you try to explain that using the same reasoning, take the base and multiply by itself 4 times, 3 times, what would you do here? That simple way of thinking of powers sort of breaks down. You're not able to use that same explanation to explain what 10 to the power of 0 equals. Now a lot of people just memorize. I know what 10 to the power of 0 is because my teacher told me. Well, I want you to, rather than just rely on what somebody told you, I want you to try to see if you can figure out what 10 to the power of 0 must be equal to. Look over here at these numbers here, 10,000 and then 1,000. How do you go from 10,000 down to 1,000? Well, one way to think of it is you would divide by 10. And to go from 1,000 to 100, you divide by 10. To go from 100 down to 10, you divide by 10. So you notice that as we go from 10 to the 4, 10 to the 3, 10 to the 2, 10 to the 1, we're simply dividing by 10 each time. Well then, by that same reasoning, 10 to the power of 0 should equal 10 divided by 10, which gives you what? 10 divided by 10 is 1. So 10 to the power of 0 is 1. All right? And now you can understand why it has to equal 1. Well, let's keep going. 4, 3, 2, 1, 0. What if you had 10 to the power of negative 1? Right? If we keep that pattern going, 4, 3, 2, 1, 0, negative 1. The middle school explanation of taking the base 10 and timesing it by itself a certain number of times certainly would not work here when the exponent is a negative 1. You may not have seen negative exponents before. But how can you explain what that would equal? Well, let's just keep doing what we're doing here. Divide by 10, and you get 1 over 10, 1 divided by 10, which as a decimal is 0.1. So 10 to the power of negative 2, dividing by 10 again, would be the same as 1 over 100. Now 1 over 100 is the same as 1 over 10 to the power of 2. And that's going to give you 0.01 if you did that on a calculator. and 10 to the negative 3. Divide by 10 again, and now you'll get 1 over 1,000. Well, 1,000 is 10 to the power of 3. We saw that up above. So 1 over 10 to the power of 3, which is going to be 0.001. So notice what happens when you have negative exponents. 10 to the negative 3 is the same as 1 over 10 to the positive 3. 10 to the negative 2 is the same as 1 over 10 to the positive 2. 10 to the negative 1 is the same as 1 over 10 to the power of 1. So a negative exponent seems to mean simply take the reciprocal of the power. So 10 to the negative 4 would mean take the reciprocal of 10 to the positive 4. And 10 to the positive 4 on a calculator is 10,000, so that's going to be 0.0001. Now notice another observation. When the exponents on the power are positive numbers, the number written in standard form, these numbers over here, are pretty big. 10 to the positive 4 is 10,000. 10 to the 3 is 1,000. So positive exponents represent large numbers, bigger than 1. 10 to the power of 0 is 1. And when you have negative exponents, the result is a number less than 1. They're small numbers. So 10 to the negative 5 would end up being a very small number. All right? So negative exponents will always represent small numbers, while positive exponents will always represent very large numbers when they're in powers. Okay? So that's a bit of a review of powers. Let's now move on to scientific notation. Scientific notation is used to write large numbers or small numbers, typically, but it can be used for any number you like. For example, let's take a number like 6,200. You can write it like this. We would call this standard form, 6,200. Now notice, you could think of 6,200 and you could say, well, it's the same as saying 6,200 times 1. Right? That means the same thing as saying 6,200. But we saw earlier that the number 1 is really the same as saying 10 to the power of 0. 10 to the 0 is 1. So 6,200, as strange as it might seem, it could be written like this, 6,200 times 10 to the 0. But it could also be written as 620 times 10. That would also give you 6,200, or 10 to the 1. It could be written as 62 times 10 to the 2, or times 100, right? 62 times 100 would give you 6,200. And you can see what I'm doing here. If I keep going, we get 6.2. I'm dividing these numbers by 10, times 1,000 would give you 6,200. 6.2 times 1,000 could be written as times 10 to the 3. And there's no reason to stop. If we divide that by 10, we get 0.62. And this would become times 10 to the, you see a pattern here, times 10 to the 4. And you could play this game forever. You could say it's 0.062 times 10 to the 5. These all represent 6,200. Now here I was dividing by 10. Well, we can go up and we can multiply by 10. It's going to be the same as 62,000 times 10 to, can you guess what power this would be, times 10 to the power of what? Well, look at the pattern, 4, 3, 2, 1, 0, times 10 to the negative 1. That would also equal 6,200. So there are all these different weird ways of writing the number 6,200. 6,200 is the standard way to do it, the standard form, but these are all legitimate ways of representing the same number. Now, one of these ways is called scientific notation. Can you guess which one here represents scientific notation? Well, in proper scientific notation, the number out front in front of the power has to be a number between 1 and 10. It could be a 1, and it has to be actually less than 10. It can't actually equal 10. So it's got to be 1 or larger and less than 10. Well, which one of these numbers is between 1 and 10? Well, it would be this guy here. 6.2 is between 1 and 10. So if you wanted to write 6200 in scientific notation, you'd write 6.2 times 10 to the 3. Now, how would you get that answer in scientific notation without doing all of this pattern here? Well, look back at the number 6200. If you wanted to write it in scientific notation, its decimal is over here at the end right now, 6200 with a decimal at the end. You would move the decimal until you get a number between 1 and 10. So if it's 6200, the number that ends up being between 1 and 10 would be 6.2. So I'd have to move the decimal 1, 2, 3 places to get 6.2. And then because I moved it 3 places, we ended up multiplying by 1,000, or 10 to the positive 3. Now, why is it positive 3? Well, as we saw earlier, when the exponents of powers are large, positive numbers, the numbers are big. When the exponents are negative numbers, the numbers are small. So because 6200 was a big number, the exponent over here is positive 3. Okay, try another example. Suppose you have the number 78,500, and you're asked to write that in scientific notation. Well, the decimal initially is at the end of the number. Looking at these digits, what number could you make from, just by moving the decimal, could you make that would end up being between 1 and 10? Well, to be between 1 and 10, it looks like it's going to be 7.85. To get 7.85, you have to move the decimal 1, 2, 3, 4 places. So in scientific notation, this ends up being 7.85. There's my number between 1 and 10. And because I moved the decimal 4 places, times 10 to the 4, and because it's a big number, 78,500, it's positive 4. Now, what if you had a small number? Suppose you have 0.00231. Okay, and you want to write this in scientific notation. Well, the decimal right now is over here. So to get a number between 1 and 10, what number would we end up with if we move the decimal? Well, this time we're going to have to move it to the right. And we're going to get a number in the end, 2.31. 2 decimal 31 would be between 1 and 10. So let's move it 1, 2, 3 places. So this is going to be 2.31. There's my number between 1 and 10. Times 10 to the 3, because I moved 3 spaces. But this is a small number. It's less than 1. Then the exponent over here has to be negative 3. All right? Now, some teachers teach a way of remembering this that personally I don't like, but if you've been taught this, it's okay. They would say when you're moving the decimal to get scientific notation, if you move it to the left, like we did in that example there, the exponent is positive, and if you move it to the right, like we did here, the exponent is negative. If you like to memorize that, that's fine. Personally, I prefer the understanding that when this number was big, the exponent, the power of 10, will be positive. When the number is small, the power of 10 will be negative. To me, that's a bit of a better way of understanding it. Let's do one more example. Well, actually, why don't we go backwards? Suppose you have a number that's already in scientific notation, 5.5 times 10 to the 6, and you're asked to write that in standard form. Well, you can tell right now that because the power is positive, this is going to be a big number, right? So 10 to the power of 6 means we have to move the decimal 6 places, right, to get back to standard form. So right now the number is 5.5, so let me write 5, and the decimal was here, so we have to move it 6 places, and it's going to be a big number, so I'll move to the right to get a big number. 1, 2, 3, 4, 5, 6 places. Now I'll put zeros in. There we go. The number ends up being 5,500,000. Now you don't need to put these little curly numbers underneath, these little curly signs underneath. You can eventually just add the zeros without doing this scribbling underneath. Suppose you had a number like, well, let's say 6.5 times 10 to the negative 4. Well, you know negative 4 means this is going to end up being a small number, right? So being a small number, we're going to move this decimal not to the right, which would give me a larger number when I tack on zeros. We're going to move it to the left, and we'll put zeros in front. So we'll get 0 point. Now how many spaces do I move the decimal? Well, 4 places. 1, 2, 3, 4. So I'm going to end up getting 3 zeros in front, and then 65. Just do a quick check. If you switched this back, 1, 2, 3, 4 places, 6.5, times 10 to the negative 4, because we moved it 4 spaces, that's correct. All right, so I hope that helps. You should now be able to do the worksheet. If you're in grade 9 science, you should be able to do this worksheet, which is in your yellow booklet, converting numbers that are in standard form to scientific notation, and then converting numbers back to standard form, or written here as expanded notation, which is the normal way of writing it. All right, so I hope that helps. Good luck with scientific notation, one of your easy first assignments in this course.